In mathematics, the gradient is a generalization of the usual concept of derivative of a function in one dimension to a function in several dimensions. If f is a differentiable, scalar-valued function of standard Cartesian coordinates in Euclidean space, its gradient is the vector whose components are the n partial derivatives of f. It is thus a vector-valued function. Similarly to the usual derivative, the gradient represents the slope of the tangent of the graph of the function. More precisely, the gradient points in the direction of the greatest rate of increase of the function, and its magnitude is the slope of the graph in that direction. The components of the gradient in coordinates are the coefficients of the variables in the equation of the tangent space to the graph. This characterizing property of the gradient allows it to be defined independently of a choice of coordinate system, as a vector field whose components in a coordinate system will transform when going from one coordinate system to another. The Jacobian is the generalization of the gradient for vector-valued functions of several variables and differentiable maps between Euclidean spaces, or, more generally, manifolds. A further generalization for a function between Banach spaces is the Frechet derivative. Motivation. Consider a room in which the temperature is given by a scalar field, T, so at each point the temperature is T. At each point in the room, the gradient of T at that point will show the direction the temperature rises most quickly. The magnitude of the gradient will determine how fast the temperature rises in that direction. Consider a surface whose height above sea level at her point is h. The gradient of h at a point is a vector pointing in the direction of the steepest slope or grade at that point. The steepness of the slope at that point is given by the magnitude of the gradient vector. The gradient can also be used to measure how a scalar field changes in other directions, rather than just the direction of greatest change, by taking a dot product. Suppose that the steepest slope on a hill is 40%. If a road goes directly up the hill, then the steepest slope on the road will also be 40%. If, instead, the road goes around the hill at an angle, then it will have a shallower slope. For example, if the angle between the road and the uphill direction, projected onto the horizontal plane, is 60 degrees, then the steepest slope along the road will be 20%, which is 40% times the cosine of 60 degrees. This observation can be mathematically stated as follows. If the hill height function h is differentiable, then the gradient of h dotted with a unit vector gives the slope of the hill in the direction of the vector. More precisely, when h is differentiable, the dot products of the gradient of h with a given unit vector is equal to the directional derivative of h in the direction of that unit vector. Definition. The gradient of a scalar function f is denoted f, or where denotes the vector differential operator, del. The notation, grad, is also commonly used for the gradient. The gradient of f is defined as the unique vector field whose dot products with any vector v at each point x is the directional derivative of f along v. That is, in a rectangular coordinate system, the gradient is the vector field whose components are the partial derivatives of f, where the a are the orthogonal unit vectors pointing in the coordinate directions. When a function also depends on a parameter such as time, the gradient often refers simply to the vector of its spatial derivatives only. In the three-dimensional Cartesian coordinate system, this is given by where I, j, k are the standard unit vectors. For example, the gradient of the function is gradient and the derivative or differential. Linear approximation to a function. The gradient of a function f from the Euclidean space n to at any particular point x0 in n characterizes the best linear approximation to f at x0. The approximation is as follows. For x close to x0, where is the gradient of f computed at x0, and the dot denotes the dot products on n. This equation is equivalent to the first two terms in the multivariable Taylor series expansion of f at x0. Differential or derivative. The best linear approximation to a function at a point x in n is a linear map from n to which is often denoted by dfx. or df, and called the differential or derivative of f at x. The gradient is therefore related to the differential by the formula for any Vn. The function df, which maps x to dfx, is called the differential or exterior derivative of f and is an example of a differential one form. If n is viewed as the space of column vectors, then one can regard df as the row vector with components so that dfx is given by matrix multiplication. The gradient is then the corresponding column vector, i.e., gradient as a derivative. Let U be an open set in Rn. If the function f UR is differentiable, then the differential of f is the derivative of f. Thus f is a function from U to the space R such that where is the dot product. As a consequence, the usual properties of the derivative hold for the gradient. Linearity. The gradient is linear in the sense that if f and g are two real-valued functions differentiable at the point Rn, and alpha and beta are two constants, then alpha f plus beta g is differentiable at a. And moreover, product rule: if f and g are real-valued functions differentiable at a point Rn, then the product rule asserts that the product fg is differentiable at a. And chain rule: suppose that f R is a real-valued function defined on a subset A of Rn, and that f is differentiable at a point A. There are two forms of the chain rule applying to the gradient. First, suppose that the function g is a parametric curve, that is, a function g. Irn maps a subset Ir into Rn. If g is differentiable at a point Ci such that g equals A, then where is the composition operator? Equals f. More generally, if instead IRK, then the following holds, where T denotes the transposed Jacobian matrix. For the second form of the chain rule, suppose that h Ir is a real-valued function on a subset I of R, and that h is differentiable at the point Fi. Then further properties and applications. Level set. Say level surface, or isosurface, is the set of all points where some function has a given value. If f is differentiable, then the dot product xv of the gradient at a point x with a vector v gives the directional derivative of f at x in the direction v. It follows that in this case the gradient of f is orthogonal to the level sets of f. For example, a level surface in three-dimensional space is defined by an equation of the form f equals c. The gradient of f is then normal to the surface. More generally, any embedded hypersurface in a Riemannian manifold can be cut out by an equation of the form f equals 0 such that df is nowhere 0. The gradient of f is then normal to the hypersurface. Similarly, an affine algebraic hypersurface may be defined by an equation f equals 0, where f is a polynomial. The gradient of f is 0 at a singular point of the hypersurface. At a non-singular point, it is a non-zero normal vector. Conservative vector fields and the gradient theorem. The gradient of a function is called a gradient field. A gradient field is always a conservative vector field. Its line integral along any path depends only on the endpoints of the path, and can be evaluated by the gradient theorem. Conversely, a conservative vector field is always the gradient of a function. Riemannian manifolds. For any smooth function f on a Riemannian manifold, the gradient of f is the vector field f such that for any vector field x, where gx denotes the inner product of tangent vectors at x defined by the metric g and xf, is the function that takes any point xm to the directional derivative of f in the direction x, evaluated at x. In other words, in a coordinate chart phi from an open subset of M to an open subset of Rn is given by where xj denotes the jth component of x in this coordinate chart. So, the local form of the gradient takes the form. Generalizing the case M equals Rn, the gradient of a function is related to its exterior derivative, since more precisely, the gradient f is the vector field associated to the differential one form df using the musical isomorphism defined by the metric g. The relation between the exterior derivative and the gradient of a function on Rn is a special case of this in which the metric is the flat metric, given by the dot product. Cylindrical and spherical coordinates. In cylindrical coordinates, the gradient is given by where phi is the azimuthal angle, z is the axial coordinate, and d rho, e phi and ez are unit vectors pointing along the coordinate directions. In spherical coordinates, where phi is the azimuth angle and theta is the zenith angle. For the gradient in other orthogonal coordinate systems, see orthogonal coordinates. Generalizations. Gradient of a vector. Since the total derivative of a vector field is a linear mapping from vectors to vectors, it is a tensor quantity. In rectangular coordinates, the gradient of a vector field F equals is defined by where the Einstein summation notation is used and the product of the vectors A, X is a dyadic tensor of type, or the Jacobian matrix. In curvilinear coordinates, or more generally on a curved manifold, the gradient involves Christoffel symbols, where G, J, K are the components of the metric tensor and the A are the coordinate vectors. Expressed more invariantly, the gradient of a vector field F can be defined by the Levi-Civita connection in metric tensor, whereas the connection